Hello, everyone. My name is Jordan Johnson from Group B, and this is our final presentation for our smart parking system. Our group consists of three computer engineers being Oscar, Kuna, M. Ridwan, and Kyle Carpenter, and one electrical engineer being me, Jordan Johnson. Our motivation for this project comes from the fact that UCS parking garages become congested during times of heavy traffic flow. This causes a number of problems, including traffic jams and safety issues. Signs indicating open or full and UCS apps that shows the percentage of open parking spots do not give enough information about what's going on inside the garage. This leads to students speeding inside the garages when they are struggling to find a parking spot, therefore creating an unsafe environment. Because of this, we have decided to design a modern parking system that will help create a safer environment inside of these garages, help get rid of traffic jams around campus, and help people be on time to classes.
All right, for goals and objectives, first we're going to use computer vision for detecting cars passing through specific regions of the garage. Next we're going to use LED displays to communicate how many open spots are available in a specific region. We want the system to be low power, but that isn't a high priority for us since the system is not going to be battery driven. We're also utilizing Ethernet for communicating between the camera, the server, and the sign display. All right. We're using a parking garage regional info system, and what we mean by this is that in specific regions we're wanting to display info, like on this LED display shown, and to kind of make it easy to figure out which specific region has a good amount of available parking spots. So we're going to have a camera detecting a vehicle passing through. It's going to figure out whether it's entering or leaving and relay that information over to the database. The database is then going to update how many spots are available, and wherever that specific spot is pointing to, it's going to communicate with that specific PCB, and then it'll update its display. There's also a GUI application which gives a breakdown and more of an overview, which makes it easy if you are not in person to know where there's going to be spots available. All right, and for the specifications and requirements, we want the system to have a max update delay of around 10 seconds, minimum brightness of 1,000 nits, which we more than meet. We want scalability. We want to be able to at least cover 100 camera PCB assemblies. And then for the camera, we want it to be at least 95% accurate for detecting vehicles entering or leaving. For the project, we did a lot of sharing different parts of the project. So Oscar, he mainly covered the Java background service and database programming, but he also helped out on a lot of the microcontroller stuff and camera programming. Ridwan mainly focused on the camera programming, but he also did some work on the database. Jordan as well was mainly focused on designing the PCB, but helped on the camera. And myself, I did a little bit of helping the PCB, but was mostly focused on the microcontroller.
Companies like Indec and ParkEagle have implemented their version of smart parking by leveraging the usage of ultrasonic sensors, surface-mounted sensors, or even ultra-low-powered sensors. To keep up with the modern world, we aim to modernize the system with the usage of computer vision and improve user experience with graphics interfaces.
So this is the overall system diagram for our smart parking project. As you can see, the system is divided in four major components: the camera, the control unit, the PCB, and LED display. The camera allows the computer vision to take place. Through machine learning, the camera determines if cars are entering or leaving a parking area. Now, this data is later transmitted to the control unit through this PoE switch. Control unit server then processes the data and display the necessary information with the help of the created graphics interface. Later, the PCB would receive this data through the PoE splitter, and all the way at the end, the LED display would display the number of parking spaces calculated with the algorithm.
One of the core components of the project is the camera integrated with computer vision technology. This portion is responsible for vehicle detection and potentially have the other components of the project work based on the data gathered from it. There were quite a few cameras that were considered for the project. One of the main considerations for the camera selection were the Oak cameras from Luxonis. Most of the Oak cameras have onboard AI processing, which allow them to run any AI models with feature tracking and edge detection. One of the main recommendations was the Oak D Pro PoE camera, which comes with two of the 12 megapixel Series 2 cameras with 4 tera operations per second capability with a wide field of view range. Oak 1 and Oak D PoE cameras are the more cost-friendly options, which also are able to run any AI models, however, with less features than the Oak D Pro PoE camera. Some much more cost-friendly options, like the IP cameras, were also considered. However, even though these cameras are much cheaper compared to the Oak cameras, they do not have onboard AI processing capabilities. Thus, the system would have to account for magnitude of data being transferred frame by frame, as well as live feed would need to be extracted from the camera via IP address, which would cause additional complexities. They also only support wall or ceiling mount, which would make the mounting process much more complex than using a tripod. Oak One PoE camera comes with a single camera with transmission speed of 1000 megabits per second. This PoE powered camera is the most cost effective in comparison to the other Oak cameras, and it also can run any AI models with feature tracking and detection. Thus, this camera was chosen for the project compared to the C800 IP camera, which does not allow onboard AI processing, or the OD PoE camera, which have too many features driving up the price, which would remain unused for the project. Luxenus provides a lot of pre-trained AI models that allow computers to detect and recognize objects and many of their properties. This is a provided demo vehicle detection from them that we're working with initially. However, the needs of the project were no longer met with this demo, and Depthia Experiments repository was leveraged. The Gen 2 People Tracker model from the repository was used as a base code and was modified as necessary. A vehicle detection model from OpenVINO was imported to replace the People Tracker model. This model tracks all the vehicles in the frame and returns information like ID and location of upper left corner and bottom right corner. With that, we detect the directions of the cars, whether it's leaving or not, with this function. As soon as the detected vehicle leaves the field of view, database is updated, which is a MySQL database. The model sends a -1 depicting one less parking lot if a car is entering, or a +1 if it's leaving.
Let's talk about the control unit now. The control unit sits between the camera and the PCV, and it has a server which keeps track of all the available spaces throughout the entire garage. It has an Ethernet switch which allows the camera and the PCV to communicate with the server, and there is a UPS or battery backup to power all these devices. Let's talk about the PoE switch now. Now, to power the cameras and the PCV, we thought that using power over Ethernet would be more cost effective than having traditional electric outlets throughout the garage. Power over Ethernet, as you may know, is a technology that allows us to inject or transmit electricity into the same cable that transmits the data. Now, deploying our parking system to an entire garage would require a switch with many ports, but a small 5-port switch was enough for a proof of concept. Now, the selected camera required PoE type 1, so we searched online for this type of switch and we found several of them as shown on the table. Now, some of these switches are type 2, but they're backward compatible with type 1 devices. At the end, we selected the most cost-effective one for $33.99. Let's talk about the UPS or battery backup now. For our project, we wanted a UPS that could keep the system running for at least 10 minutes and capable of keeping the camera, switch, and the server running while doing our tests and demonstrations. We calculated that between the PoE switch and the server, we needed about 88 watts. And we found this APC brand UPS. Now let's talk about the server. We needed 3 things for a parking system. 1, a place where to store the data captured by the camera. 2, a device to relay the data from the camera to the LED sign. And 3, a program to interact with the parking system to configure it, display the data, keep track of available spaces, etc. In other words, we needed a server that could support a database that has an Ethernet port, enough CPU and RAM capacity to run a custom program. Now, the most cost-effective computers are those that come with built-in CPU and memory and usually have no expansion slots, such as the Raspberry Pi or those shown in the table. Now, these boards are called single-board computers, and there are many options out there, although not all of them are available due to the chip's availability. Initially, we had selected the Odyssey board because we could install Windows, since we already had started developing software for a Windows machine. However, this board was on back order and we didn't want to risk not getting it on time. The other board capable of running Windows was the x86-2 Advanced Plus, but it was also in back order. Therefore, we chose a Raspberry Pi at the end. However, we started having issues with our Java program running on the Raspberry Pi, running the database and overall configuration of the Raspberry Pi. And after spending a day and a half on this board, we found yet another solution, and we switched to this B-Link mini PC that has an Intel processor and capable of running Windows, onto where our Java program and the database was able to run without issues. Now let's talk about the server software. The programming language we used to develop the server software was Java and MySQL for the database. We chose these because I had some experience working with these two in other school projects in previous courses. Now, all the parking system's data is stored in a database. The database was created using MySQL Workbench, and here are some of the tables used by our parking system. Now, the garage is divided by different levels, and each level is divided by many sections. A section is like a parking row in the garage. That's what the camera monitors. Now, each section is going to have cameras and different displays, and the camera has a camera log where the camera, every time it detects a vehicle and it sends that information to the server, it stores that into this camera log table. In addition to hosting the database, the server also runs two Java programs. The background service, which is the program that is doing all the heavy lifting of checking for updates from the camera, calculating the changes on the number of spaces, and updating the LED displays. The second program is the user interface, or GUI, which is used to monitor the parking garage system and make changes to the system, like adding a camera or a new LED sign.
We decided to design our PCB in a way such that it could receive both data and power from the PoE switch. This is accomplished by a PoE splitter as shown in the diagram below, which illustrates the flow of data and power through the various components on our board after the connection goes through the splitter. So now I'll go into a bit of detail about some of these components. First, we have the PoE splitter, which separates the PoE connection from the switch into a 5-volt connection and an Ethernet connection, which are then received by an Ethernet port and a DC plug. This 5-volt connection gets further regulated to a 3.3-volt connection such that it can safely power all the components on our board. Next, we have the MP-Lab snap-in circuit debugger, which allows us to use a serial wire debugging interface in our microcontroller and communicate with the Ethernet PHY chip and LED matrix. We also have a 50 MHz oscillator, which generates a clock signal for our Ethernet PHY chip, which then outputs a reference clock signal for the microcontroller. Next, we have the two chips that are on our board, being the TLK111 and the ATSEM E70J19A. The TLK111 is a 48-pin chip which serves as a transceiver by receiving the connection from the Ethernet port and then communicating with the media access control block on the microcontroller. The ATSEM E70J19A is a 64-pin chip which includes a MAC block for Ethernet communication and 44 GPIO pins for communication with the LED matrix. Next, we have some of the components that we've used to do prototyping, being an adjustable buck converter, an RJ45 breakout, which gives us access to all the pins on an Ethernet port, and a couple of breakout boards, which we soldered our microchips onto to give us access to all the pins on those. So now I want to go deeper into our design. And first, we have the schematic for our power input and power regulation circuit, which drops 5 volts to 3.3 volts. Next, we have the MCU, which includes connections for serial wire debugging, the LED sign, reduced media independent interface, and a single power supply input. This slide further elaborates on the MCU connections by showing how they are connected to header pins, as we will be using a 2x8 female for the LED, a 1x8 female for the debugger, and a 1x2 female for any situation where we need to erase our device firmware. Next, we have the PHY, which includes connections for the Ethernet port, reduced media independent interface, a single power supply input, and the external 50 megahertz oscillator. And to continue on the connections for the Ethernet PHY, I have the connections for the Ethernet port as well as the oscillator. This is our breadboard that we worked on in the early phases of our project, and some of the components that I mentioned in previous slides can be seen in this photo. Here is a picture of the top layer of our PCB, which includes all the major components in our design, along with some SMD components. And next we have the bottom layer, which only includes SMD components. After everything was soldered on, this is what our PCB looked like. And finally, we have a picture showing the connected hardware, including the PoE splitter and the debugger.
Let's go ahead and talk about the LED display. For the hardware, we have a 32 by 64 resolution, and it uses a 1/16 scan rate in order to push all those pixels. The LED is only driven by a few pins. There's actually only 6 data pins in total. 3 of those are RG and B for the top half of the display, and another 3 are RG and B for the bottom half of the display. It is also daisy chainable, and the way it's able to daisy chain is it acts as though the display is extended. So if two 32 by 64 displays are daisy chained, it treats it as a 32 by 128 display. Here's an overview of the software for the microcontroller. It's overall pretty simple, but the complexity is really going to be found in the drivers. From the flowchart on the right, we have a basic system where it's going to receive data from the GMAC interface. From there, and that GMAC interface is for the Ethernet. From there, when it grabs that data, it'll figure out what number is given via the data, and that number is going to be how many parking spots are available. We just pipe that over into a function to the display driver, which will then have the display driver update to a new number based on whatever number was put in, and it automatically sorts it out based on a bunch of macros we'll have defined. The main problem comes in matching pixels to characters and then maxing those pixels to pins when we're writing our own display driver. For the driver, how we figured out how to get the numbers we wanted is first we just had to trace out. We made a grid, a 32 by 64, and then we broke that 32 by 64 into 4 different sections. From there, we would basically fill in ones and zeros for ones of where we want the bit to be high, for it to actually display something on a color line, versus 0 for nothing. From there, a Python script is written and that to then automatically generate the hexadecimal we need, as shown below the picture on the right. In order to put that data in, we would just clock in the bits for the RGB lines for RGB0 and RGB1, and then we would demux to select what line we wanted. We'd have to constantly repeat this pattern in order to constantly be refreshing the display as needed. On the Ethernet side of things, in order to get it implemented, we were going to utilize an existing TCP/IP stack. And using that stack would make it pretty simple for establishing connection with the control unit. We're going to port the stack over to our microcontroller, the AT-SAM E70 J19B. A lot of the code is already available on other SAM E70s with some minor differences. We're going to just call our display number function and pipe in the data we received utilizing this stack, as shown from the flowchart previously. However, we were unsuccessful in porting this code in the end. Sadly, a lot of this code had problems in terms of compatibility with our microcontroller, or a lot of the software just could not be used in the provided IDE from Microchip, and a lot of it was sadly way too complicated in order to be able to port within the time frame. However, if we did have time, most likely we would have been able to implement the Ethernet. On for testing the design. First of all, our first test was getting the LED blinking working correctly. And here we have an example of that, just to verify that we're able to program the microcontroller at all. From there, once we had the LED driver working, we were able to display different numbers. As shown, we have different arrows, and we have different numbers. We can even do up to 3 digits of integer numbers. Ultimately, that's not going to be needed in most regions of the garage, as it only goes up to double-digit total counts of parking spots.
To test the accuracy of the vehicle detection models, multiple tests were done in the last month of development. Mostly the tests were done in UCF's parking lot C. On a smaller batch of cars in a secluded parking lot, the model was working perfectly. Just to give you a visual representation, this is a small demo of the test. As you can see, as the cars are moving or leaving the parking garage to the left, the label leaving is increasing by 1. One thing to be pointed that it doesn't detect it didn't detect anything else but the car, so any people or any other objects on the frame would not be detected. And entering cars would result in adding 1 additional cars in the entering label. However, on larger batches in more crowded parking locations, the model was failing to count some of the cars or even adding faulty numbers in the entering label vehicles. In order to solve the issue of missing cars, after multiple trials and errors, the camera angle and positioning needed to be altered. That way, the lens had better field of vision and was able to detect the cars much more accurately. For the additional counted cars, the model had to be readjusted to allow only certain portion of the capture frames to be considered. For a better visual representation, initially the camera was detecting cars in this upper region of the frame. In our system, we're accounting for the lanes immediately right in front of the camera, which are these 2 lanes, which is in the bottom of the captured frame. Thus, to tackle the issue, the detection model was changed to keep track of the bottom region of the capture frame only and completely disregard any type of vehicle detection on the top region of the frame. As you can see, as the car was leaving over here, none of the labels had changed. However, any movement over here gets detected. This is one of the edge cases where the car is able to detect both entering and leaving vehicles at the same time. None of the people are being tracked as well. Here is a numerical representation of the tests done throughout the project duration. The most significant test results are being shown over here, where the total numbers of monitored cars are 209. Many more tests had to be done along the way for better understanding of the bugs in the model and to improve the accuracy of the detection state. As you can see, the tests done on a smaller batch in a secluded parking lot resulted in 100% accuracy. But more crowded locations, the accuracy did not meet the project requirements. However, after the optimizations and the modifications stated before, you can notice the accuracy got much better at the later stages of the project with about 94.4% accuracy rate.
Here we're testing the GUI updating. The GUI refreshes by pressing the refresh button on the left. Notice how the count goes from 413 to 412 in response to the car entering the parking area. Now the live view section shows a portion of the table where the camera records car detected. Notice that the last row was updated with a -1 because there is 1 less parking spot available.
One of the goals for our project was to have a user-facing web application. However, with less development time, after speaking with the team and the advisor, it was set to be a stretch goal. Initially, the website was hosted and Figma was made. Here are some of the visual representations. In this picture, you would be able to see the available spaces, the sign-in registration, and some administration capabilities. As you can notice, the control unit server program has been implemented with the same color scheme. This is a summary of our project finances. As you can see, we needed parts for LED, PCB, power supply, splitters, and many more. However, our most significant and expensive investment was the O camera.
And here's a table of related standards that impacted our project. And thank you. This was the Smart Parking Garage System Group B presentation.